Okay, before we get into lesson 6.4 today, we're going to do a little warm-up. It's more just a mathematical concept that you just need to be aware of, and most of the time you think of it in the background without even really naming it. So what we need to know is if I have some vector x plus some vector y, and it equals vector x, we want to ask ourselves, well, what do we know then about the vector y? What does it have to be? I missed my little vector notation here, so just add that in. And whenever this happens, that I have some value x and some operation, so my operation is a little heart here, but it could be any operation, and then some value y, and it actually just equals the x, we call y the identity for that operation. And each operation that we know has a different identity. So for instance, you could be thinking about multiplication, back to just regular numbers, we're not thinking about vectors here. And when I have multiplication, the identity is 1. So you could be thinking, right, like if I have x times 1, then that's just equal to x. And if I have addition, it's a different identity. In addition, the identity is 0. And sometimes this comes up as a point of confusion for some students. Like for instance, when I have like x divided by x, some students will try and tell me that that equals 0, but it's equal to 1. And that's just a confusion about identities when they do that. And so for addition, if the identity is 0, then we see that x plus 0 is still equal to x. So it's the thing that doesn't really actually have an effect or a change. When we move into vector operations, when I think about multiplication, I could be thinking about scalar multiplication of a vector. We are going to look at vector multiplication later on in this course as well. And so if I have some vector and I multiply by some number, some value, and it doesn't actually change anything, I end up with the exact same vector, then really I'm just multiplying it by a scalar of 1. And so it's similar to the multiplication identity for just scalars. And then for vector addition, what we're talking about up here, for vector addition, it's almost the same as regular addition, except that I can't add a vector with just a number. So it can't be x plus 0 because this is a nonsense statement. It has to be the 0 vector that I'm adding, and that would give me x. So for vector addition, the identity is 0, but as a vector. All right, so that's just something we want to keep in the back of our mind. I'm not going to ask you a question directly about that. So in today's lesson, we're talking about properties of vectors, and some of these things we've already been doing, but we just want to double check, like, what are the rules here? You know that sometimes things aren't allowed. So for instance, like if I have a number times a bracket, we know that we can distribute that through, right? But if I have a bracket with an exponent, you cannot distribute this through. This is not the same as this. So we want to know, like, what are the rules? Just like up here, we know what the rules are. When can I distribute through? So let's take a look at some of the rules for vectors. So commutative property means that you can change the order when you're doing addition. So you might see some of these terms in university if you're taking some more math courses: commutative, associative, and distributive. I'm not going to ask you specifically about these words, but we do need to know the gist of the rule. So what this says, the first one, is that if I have vector u plus vector v, that's the same as vector v plus vector u. In the associative property of vector addition, that's talking about, well, what happens when I have 3 vectors? So maybe I've got vector A, B, and C, and what this one says is actually the order of the addition doesn't matter. So if I look at this string and I add these 2 first, find that answer, and then add C, that's the same as adding these 2 first, finding that answer, and then adding that onto A. I'm going to end up with the same result. So that's good to know that we can do that. We can switch the order around. The next one is about the distributive property of scalars over a vector addition. So if I have some scalar k, so no vector notation on this one, this is just a plain old number, and it's in front of some bracket, so I've got vector v maybe plus vector w, I can actually distribute this one in, so that's good to know. That's the same as doing k times vector v plus k times vector w. So a lot of these you probably would have done without thinking, but you do want to be considering it in the back of your mind. Is it okay? And then the associative law of scalar multiplication, it says if I have two scalars multiplied by a vector, I can think about this in a couple of different ways. I can think about multiplying those two scalars together first, coming up with that answer, and then multiplying it by the vector. Or I could multiply the one scalar by the vector and then multiply the second scalar by that result. And I'm going to end up with the same answer. The distributive property of vectors over scalar addition. So it's kind of the reverse of what we had above. Here we had one scalar and an addition of two vectors. This time I'm going to have two scalars being added and then multiplied by one vector. And here it's the same sort of thing, except normally we write the scalars in front, so that's the only thing that kind of makes us a little bit uncomfortable here. But really I'm distributing the vector v through this bracket, and I end up with a times v plus b times v. All right, so those are the properties. Now we're just going to work away on practicing using some of those. And again, a lot of this is going to feel like, a lot of these rules feel like just regular number math, right? It doesn't feel like it matters if it's a vector. It does, you want to think about it, but I think you guys would do this automatically. So this should feel easy, don't overthink it. We're writing the following vector in simplified form. So what we've got here is like a whole bunch of vectors that we're adding together, right? So we're going to take 3 times the length of vector A and then tack on vector B and then subtract 2 C's. I don't know what that might look like. We're going to figure out what that resultant vector is and then multiply it by 4, so make it 4 times as long. I don't know what these vectors look like. It doesn't matter. I can still combine and move this around to try to simplify this expression. So I'm going to multiply the 4 into the bracket. The properties tell me I can do this. And at the same time, I'm going to take this -1 that's in front of this bracket and multiply it through. All right, now, just like we would do with regular math, we're going to collect like terms or collect like vectors. And I know from the property above that if I have the same vector with 2 different coefficients, I can just add those coefficients together and put them in front of one of those vectors. So here I have vector A with a 12 coefficient and vector A with a -1, so I can just put the 12 and the -1 together in front of my vector. So I get 11 times vector A. And then we'll do the same thing with vector B. And again, this would feel automatic. You would just do it. 4 minus 5 gives me -1 in front of vector B and -7 in front of vector C. And that's it for this question. We've simplified this now. I could, if I now knew what vector A, B, and C look like, I could draw that triangle and connect and find the resultant vector. All right, in example 2, this one's a little bit different. We're going to be moving into looking at these vectors I, J, and K. There's some special vectors, but it doesn't matter really what they are just now. What I want to do is take these 3 vectors, so I've been given 3 vectors, X, Y, and Z, and they gave me an expression for them in terms of I, J, and K. So each of those have been written out in terms of I, J, and K. What I want to do is find a new expression for this vector. This is just one vector if I were to draw it out and connect it and then draw in the resultant, right? So I want to figure out what this vector is, but in terms of I's, J's, and K's. So what we're going to do is start with this expression here that we're trying to simplify. And I'm just going to substitute in for each one of these original vectors x, y, and z what they are in terms of I, j, and k, and then we'll try to simplify. So I know that x is the same as 3i minus 4j plus k, and then I'm going to add 2 y's. So I'm going to do 2 times vector y was j minus 4k. And then we're going to subtract z. So I am subtracting z in a bracket so that I don't forget to flip all of the signs here. And now I could try to simplify this. I'm going to bring the 2 into this bracket, and at the same time I'm going to bring this -1 into this bracket here. And then I'm going to collect like terms again. So I'm looking for my I vectors. So sometimes a highlighter can help here. Scanning through, there's my I's, there's my J's, and there's my K's. So we'll collect all of our like terms here. I have 4 I's, and then adding up my J's, I get 0J. And then adding up my K's, I get -12K. And then, of course, 0J, that's just 0, so I don't actually need to write that. I can just write 4I minus 12K. All right, moving on to the last example. In this example here, what I've been given is vector A and vector B in terms of x's and y's. But the question's asking me to find x and y in terms of A and B. So really important that you can understand what this question's even asking you for. It's asking you to write x in terms of A and B. And then it wants the same thing for y. So I also want to do y is equal to stuff with A and B. So I'm trying to just reorganize these 2 equations here. And there's a couple of different ways that you could try this. What we're thinking back to is grade 10 math when we solve systems of equations by substitution or elimination. So I'm going to use elimination to do this. I'm going to call this first one vector, or equation 1, and this second one equation 2. And when we use elimination, what we're looking for is we're trying to eliminate either the x's or the y's. So I'm going to stack these 2 equations on top of each other, and I'm going to try to eliminate I'm going to choose to try to eliminate the y's because I find that these coefficients are more similar. So I want the coefficients to be the same number. I don't care if the signs match though. So all I need to do is take this equation here, and I wish that this was double. So I'm actually going to double all of the terms in this equation. So I'm going to take equation 1 as it is. And then I'm going to do 2 times equation 2. So just some communication off in the green writing. I would want you to include that. And so now I'm doubling all the terms. And now my goal here is to eliminate either the x's or the y's. I chose to match the y's, so that's what's going to get eliminated. And then I need to ask myself, well, what I want to do with these equations to eliminate the y's. And it's going to be adding or subtracting. So here I just ask myself, like, which operation is going to make the y's go away? And in this one, it's going to be addition. So I'm adding these 2 equations. I'm going to add up all of the stacked columns. So over here, I end up with A plus 2B. And over here, I get 11x. And then again, the y's were eliminated. So I'm almost there. I almost have x is equal to some stuff with a's and b's. I just need to divide everything by 11. And there we have it. That's one of the 2 answers that they asked me for. Now I have to go and get the other one that they were asking me for. And again, I have a couple of choices. I could go back and redo this exact same process, but trying to make the numbers in front of the x's match. Or now that I have one equation in terms of x, I can substitute this into either equation 1 or equation 2. So that's what I'm going to do here. I'm going to call this equation 3. And I'm going to sub 3 into, and I get to choose here which one I want. It doesn't really matter to me because none of these coefficients on x is going to make this really nice and easy when I plug it in, but I might scan ahead to see if one looked a little bit easier than the other. So I'm going to plug it into 2, and so I'm doing 3 times the x expression. So instead of putting an x in here, I'm going to fill it in with this. Oh, sorry, plus. And then plus 2y's. So there we got b plus 3 times the x bracket plus 2y's. And now we're going to simplify out. And again, my goal here is to get y is equal to some stuff with a's and b's. So I'm going to rearrange this, the y is by itself. So I want to get the y all by itself here. We'll bring over the a. We've got this plus b that's already there, and then we'll subtract away 6/11ths of a b over here. And then we can simplify this. This is 1b is the same as 11/11ths, and so 11 minus 6/11ths is 5/11ths. And then my equal sign's kind of in a weird spot there. And then finally I need to divide everything by 2, so that just means it's going to join the 11 as a multiplier over here in the denominator. And there's my second equation. Now, again, there were lots of different choices for me in this question. I could have done, instead of substitution over here for my second method, I could have done another elimination. I like elimination better. It seems a little cleaner and faster for me. Or I could have done 2 substitutions from the beginning. So I could have rearranged, say, equation 1, so it looked like x equals some stuff with a's and y's, and then I could have plugged it into 2, and I would have had only a's, b's, and y's. Then I could have rearranged it, and then I would have to back substitute to find x. So again, I have a couple of choices there. All right, in the homework, for page 307, number 5, it's just a really confusing question, the wording of it, like what are they even asking you to do? What they're asking you to do is take this expression and play around with it, rearrange it, and try and use some properties that we just learned about to prove that it actually is the same as PQ. So you're going to start with this expression here, and you're going to show that it equals this thing. Okay? Have fun with that homework.